right, I think we can get started. So today it's a pleasure to have Matteo Fasiello from Madrid, and he will tell us about how to probe the LE universe with primordial messengers.
Right, thanks. Thanks, Raffaele. I think, yeah, the microphone is working, so let me start by thanking the organizers for the opportunity to give this talk, which is going to be on, testing the LE universe with primordial messengers. And by LE universe, I'm going to mean today, essentially the very early universe, so I'm going to mean inflation. And so let me remind you of something that you already know. We need to accelerate the universe early on, one reason being to explain CMB observations at the very least. There's many ways to do it. The simplest one is to have a potential associated to a single scalar field that looks like, essentially for a sufficiently long time, looks like a cosmological constant, but then of course it needs to give way to a radiation domination, matter domination, and so on and so forth. So we just need a simple potential that's constant for a sufficiently long time, and then it's steep enough to end the acceleration, to end inflation, and that will do the job. That single field through roll inflation, one way to realize it is just to use a very simple scalar field. So this does the job. It might appear like a cartoonish picture, but it is a sufficiently efficient way to work this out. Now, let me make this a little bit more quantitative here. So we want the potential to be flat, and the immediate condition is on the first derivative of the potential, and that's how we identify the first low roll parameter. And of course, we want this potential to stay flat, again, for a sufficiently long time that inflation lasts long enough to explain, as I said, CMB observations. We obtain that by, well, adding another condition, and we want this potential essentially to stay flat. We apply this condition on the second derivative of the potential. That single feeds through roll inflation for you. It does the job very well. In fact, we don't need to worry at all about having a background solution. We can go straight to fluctuations. And as soon as we consider fluctuations, let me just remind you that these quantum fluctuations are actually very important, not just for the very early universe, but also because they provide the seed for for temperature fluctuations at the CMB, but also for structure formation and structure evolution. So this is really rather important. Now let's get to the point here. We are inflating. We are inflating with a single scalar field. So we've got the degrees of freedom counting that's very simple. We've got GR as our theory of gravity plus a scalar field. So that's 3 degrees of freedom. We're going to have 2 Fs to study fluctuations in appropriate whatever gauge you want. At the end of the day, everything is gauge invariant. So we've got scalar fluctuations atop this FRW metric and tensor fluctuations, in other words, gravitational waves. So this is what we have to contend with. And we want to characterize these scalar fluctuations and tensor fluctuations. What do? Well, we typically calculate endpoint functions, starting with the 2-point function. And this is what we get. Let's see if we focus on the scalar side of things in single fields for roll. So let me just stress here that I'm talking about the minimal scenario for now. If we focus on that, well, the expression is extremely simple. It's just a matter of identifying the Hubble rate and this roll parameter here. The k-scaling is also extremely simple. It's proportional to parameters that by now you know, the roll parameters. So thankfully, we have a number associated to this p zeta, and we get that from temperature fluctuations of the CMB, and this number is 2 times 10 to the minus 9. So if we can actually solve this. 2 times 10 to the minus 9 is on the left-hand side, then we can solve this as a function of the Hubble rate or the roll parameter, whichever one you want from scalar fluctuations. Now, if we go to the tensor side of things, things are even simpler. This expression is just a function of the Hubble rate, but we don't have a number associated to it because we haven't yet detected primordial gravitational waves. So for a while, it looked like we did, but we didn't. So we've got the vacuum fluctuations here. The tilt is just as simple. It's minus 2 epsilon. Again, in the minimal scenario, another name for it is vacuum fluctuations. So you've got this quantity, no number associated to it, so we just have an upper bound, and it's usually phrased not as a function of p gamma, but p gamma over p zeta, tends to the scalar ratio. Remember, we know p zeta, the number at least, we don't know p gamma, but we know a lot. The upper bound now, thanks to the bicep update, it's 0.035, and in the future, we're going to cross some threshold 10 to the minus 2 very soon, CMBS3, 10 to the minus 3 with CMBS4, and I should also mention with LIGHTBIRD, the Japanese satellite. All right, so that's what we can look forward to. And actually, let me just tease you a little bit with these numbers. When I say we're going to cross qualitative thresholds, what do I mean by that? So let's say that I want to be naive here in a single phase roll in S-1, to which we can associate the number, remember, 0.96, etc., is equal to -2 epsilon minus theta. If I say, well, I don't know nothing about epsilon or eta, then they might as well put them to be the same. If they're the same, then R is larger than 10 to the -2. This is, of course, rather naive. But from another point of view, we are actually going to cross important thresholds, R of order 10 to the -3, so CMBS4 and light, but I remind you. And it's compelling because, for example, we're going to be able to rule out, or ideally rule in, Starobinsky inflation. And that's a compelling model. It's easy to embed it in, let's say, supergravity models. And in general, from the top-down perspective, it's a natural model to play with. Starobinsky inflation is also related to Higgs inflation, large field limits. And here you get that 1 minus ns is fixed by the number of e-folds, and R is completely fixed by, once you take care of this bit, then R is fixed to be 2 times 10 to the -3. And so CMBS4 or light, we're actually going to reach this threshold, making it quite an interesting feat. Now, all I've said to you so far has to do with single field inflation. So you might ask, how is it doing when it comes with the data? Now, the first plot is the, again, R versus NS plot, which was given by Planck in 2018. And this is the updated plot. And you can see that some models are doing very well. Single phase for all models are doing extremely well. Some of them not so well anymore. So for example, the violet band here, that's a natural inflation, which is not doing too well. But Starobinsky, you can see it here, is doing spectacularly well still. So single field inflation is, or some of the models are still very, very healthy. But what I'm going to try and convince you about in the coming slide is that we need to go beyond the single field picture. All right, so why should we even try to do that? Well, the first reason has to do with what we will all tempted to say, were we to detect primordial gravitational waves. So if we do see anything like that, we're going to say, oh, wait a second. As I mentioned before in the previous slides, in single field roll, you can read off R, you know the value for R, you're going to say, oh, I know P gamma, therefore I know the Hubble rate, therefore I know the energy scale of inflation. If you want to be precise, right, the energy scale of inflation is the square root of MP times the Hubble rate. But that's really too much. It will mean that we're going too far, because that presupposes the fact that we believe that single field roll inflation is the only possible model. And in order to make an extraordinary claim, which would be the fact that we know the energy scale of inflation, we do require extraordinary evidence. And that evidence also comes from the fact that we should characterize multi-field inflationary model and rule them in or rule them out, especially the most compelling one. So that has to do with interpreting observations, if we ever detect primordial gravitational waves in the coming future. The other point of view, which really stresses the idea that multi-field inflation is actually very important to test and to explore, is the fact that from the top-down perspective, say string theory, you've got too many space-time dimensions, you've got to compactify. On the process of compactifying, you end up with 4D action with many moduli fields. Now, these typically are scalar fields only, but they make the point that typical string theory embedding of the inflationary mechanism actually come with multiple fields, not just single field inflation. So from this point of view, multi-field is more likely. But that would not be enough for us to study them. But what's important is that actually multi-field inflation is actually testable. And all the coming slides will be about this, the fact that we can test for extra fields during inflation. So this is a context beyond the single field scenario, is a likely scenario, and it's a testable one. And this is really all I want to stress today. There's plenty that we can find out about the early universe from studying, for example, just primordial gravitational waves. Now, there's many directions that I could take in order to make this point, but I'm going to take a very specific one today, and I don't think I'll get to generalize away from actual inflation. So I'm just choosing, just because I like it, one specific class of models to try and make my point stronger. So this class of model is known as actual inflation, and again, we could go through several probes, but I think for the purposes of this talk, it's enough to just focus on primordial gravitational waves. I could talk about, for example, scalar non-Gaussianity, mixed non-Gaussianity, and so on and so forth, but let's just stick to primordial gravitational waves for the time being. So let me start with a model that already mentioned earlier on, it's actually excluded by the data. This is natural inflation, but it is a very compelling model. Now, why is that? Well, first of all, it's very simple. So we've got GR plus a scalar field with a specific potential. This is an axion-like potential. Now, remember, this goes back to the, I think, late 80s, early 90s. This potential, you can see it essentially as an unperturbed correction on top and over the rise flat potential. It has an approximate shift symmetry. So in this sense, you can call it a natural inflation model. And I remind you that the problem here is the eta problem, the fact that the inflaton mass, we don't want it to be too large, or we want it to receive only small correction from small quantum corrections. Otherwise, inflation doesn't naturally last long enough to explain the observations. And well, this model is viable for the axion decay constant being larger than Planck mass, at least in principle, because otherwise it's just too steep for us to obtain the right n(s)-1. But even if we let F be trans-Planckian, still, thanks to, I would say, Planck 2018 or actually BICEP these days, this model is actually ruled out. But it's nevertheless compelling from the top-down perspective. So let me write it down and go a little bit further. Let me talk about Chromo natural inflation, which is an addition on top of the natural. So this is the natural inflation model. You can see it's exactly the same as before, but now there's another sector. This is a gauge sector. And let me immediately specify that this is an SU2 gauge sector. So what's going on here? Remember the action, the natural inflation model was, the potential was too steep. And one way to effectively make it flatter is to add a friction term for the axion inflaton, and the friction term is coming through this Chern-Simons type coupling. So you write this down, and even if the axion would like to roll out the potential very, very quickly, because there is a dissipating channel for all its kinetic energy, it ends up being actually very interesting. You get sub-Planckian axial decay constant that does the job, and as a byproduct of the fact that this is an SU2 gauge sector, you get a very interesting gravitational wave signatures. Now, this model is very well studied. It's known as Chromo natural inflation, was put forward first by Atzad and Weimann not too long ago. But this model too actually ends up being in tension with the data. This is not ruled out, but it is in tension with the data. Now, because we really, really like the interesting gravitational wave features of this model, the gravitational wave phenomenology, we try to rescue it as quickly as possible. And what you do when you press for that is you just add an extra scalar sector. Why is that? Well, the reason is the following. So here, remember, we are coupling the axion inflaton to a gauge sector in order to make the potential effectively flatter. This works, it works very well. In fact, you crank up the coupling with the gauge sector, here this lambda. For lambda sufficiently large, everything works out very well. So your scalar spectral index is precisely what you need it to be in agreement with observations. But at the same time, because you've got gravitational wave signatures, which we're going to go into, you end up overproducing gravitational waves for the correct lambda. So something is going to give, and what gives is actually the fact that this axion is there, but we don't ask it anymore to inflate. We just ask it to be there and be an axion or an axion-like particle, do the job that it wants to do. But the job of inflating, we give it upon another field, another scalar field, which we call the inflaton. What are we going to lose? Well, we've got an extra degrees of freedom. We wouldn't like to have so many degrees of freedom. Ideally, we would like to stay minimal, but in order to make it work, this is one way out of the problem, and this is still a graduate that we considered. Again, we've got a sub-Planckian axial decay constant. It is observationally viable now, but what I want to focus on now is the fact that we do have an interesting gravitational wave spectrum. And what do I mean by that? Well, let me go a little bit slower now. So remember, we've got an FRW metric. We want to consider tensor fluctuations. The usual properties applied, even the one that you have in single field roll inflation. You've write down your wave equation here, okay? Now, let me remind you that on the right-hand side, you've got sources, and even in single field roll, you do have something non-zero here. You typically get something coming from scalars. Remember, you've got something proportional to zeta squared here. It's coming from the cubic Lagrangian gamma zeta zeta. Now, this is a small contribution in single field roll, so you can actually neglect it. Just solve the homogeneous equation. You've got your vacuum fluctuations. You've got your P gamma. And this is exactly the P gamma that I showed you early on in the previous slide, proportional to h squared over mp squared, and you're done. This is single field slow inflation, whilst in the case of Chromo natural, extended Chromo natural, in general, multi-field inflation, something much more interesting can happen here on the right-hand side because now you've got non-trivial sources. So how about the non-trivial sources in our case? All right, let me remind you the Lagrange that we're playing with is this one, and the coupling with the gauge sector. Now, the gauge sector is an SU2 gauge sector. You write it down whichever way you want. You choose your gauge, you do things properly. But because it's an SU2 gauge sector, you've got a couple of things working for you. The first one is that you have an isotropic solution. Now remember, if you have a U1 gauge field there, but that automatically identifies specific direction, so you don't have an isotropic solution. You have an anisotropic solution, so you need to be a little bit careful about the value of this anisotropic background, otherwise you can switch it off. In the case of the SU2, and this goes back to work by Sheikh Jabari and others, earlier than chromological inflation. In the case of an SU2, you can actually have an isotropic solution, and they've proven even back then that this is actually an attractor solution as well. So you've got an isotropic background, which is what you want. You can solve for F for W. Everything works very well. And as a result of the fact that you have an SU2, you actually end up with tensor degrees of freedom in the gauge sector. So you've got a TAJ here, or TIA, whatever. You've write it down in the wave equation, you immediately find out that, of course, now this TIJ, these tensors in the gauge sector can source gravitational waves linearly. So you don't need any loop of anything. You can just see what goes on linearly, right? So this is your wave equation now. And in case you ask, remember that, of course, you're going to have contribution to the wave equation from the inflaton sector scalars here, which is going to be nonlinear, though. You've got the same thing over here, which is going to be nonlinear, but it is pretty much subleading with respect to what this TIJ can give you. And as a result of having TIJ, you end up with P source, possibly larger than P vacuum. So this is possible, yes. No worries.
Yeah. So now you have three fields: the inflaton, the axion, and the gauge boson. And you didn't really explain what they are doing during inflation. Which one are in slow roll? Which one fluctuates around a wave or around the fundamental state?
Yes. So in fact, let me actually go back. So here, this is before I add the so-called inflaton sector. So here, who's the inflaton? We've got an axion who's also inflaton. It's rolling down. It's doing its job. We want the potential to be flat. We can do it, but we end up overproducing gravitational waves. Now, in this other approach, the axion-like particle can go down its own potential for a while. I mean, it can do whatever it wants. It's just that it doesn't need to be the inflaton anymore. The leading contribution to the energy density is coming from the inflaton. So this guy can go down its potential, and it gives us the freedom to have, as we shall see, a bump-like feature, for example, for primordial gravitational waves or not, but the axion is not the inflaton anymore, so we are paying the price right away, right? I mean, the approximate shift symmetry is here. It's not here, not necessarily. Is it a natural model? It depends, right? We're working on making it natural, but there is a price to pay, and we're already paying it. But I'll get to the advantages, though. But so, yeah, this is entirely driving inflation, entirely responsible for an S-1. We keep this sector because it's going to give us an interesting gravitational wave phenomenology. Yes, so F, yes, indeed. So F has a wave. It can have a wave in the SU2 case. In the case of a U1, you need to switch it off because otherwise you have a preferred direction. Yes. So indeed, so we've got a non-trivial background value here. We're going to source gravitational waves because of this TIJ, the tensor fluctuation in the gauge sector. Oh, sorry. Yes. So let me write down more specifically what's going on. And before that, let me apologize. I'm using psi here. I should be using gamma. Psi and gamma are related. They are essentially one. Psi is gamma over A, the scale factor. And I'm using psi just to conform with notations in a lot of papers. But this is the metric, the equation of motion for the metric, which is being sourced linearly by this TIJ, the gauge degrees of freedom, the tensor degrees of freedom in the gauge sector. And of course, T, right-handed or left-handed, doesn't matter, has its own equation of motion, which is sourced by psi. Okay, so these are the equations of motion for our system. Let me say a couple of things. First of all, here, as it turns out, T is of course sourced by the metric, but this term ends up not being relevant. Therefore, this is even easier to solve. So Tij or Tr left, we're going to solve for it, the left-handed component and the right-handed component. Now, crucially, because of the Chern-Simons type coupling, you find out that in writing down the equation of motion, even before solving for this system, when you write down the equation of motion and ignore this bit, ignore the right-hand side, you catch up with a different sign depending on your problem in the right-handed or left-handed polarization. So you've got a different solution for T left and for T right. Okay, who cares? Well, this is going to be relevant because if your leading contribution to gravitational waves is coming from T, then having T left different from T right will correspond to having psi left or gamma left different from gamma right. So you're going to end up with a chiral gravitational wave spectrum. And this is relevant, and this is something that you can test for. And let me stress that this is all coming from the Chern-Simons type coupling, and we'll see about that. So what does this mean? Well, I'm plotting the metric, and the tensor in the gauge sector as a function of time. X is k tau. Remember, 1 is the horizon, smaller than 1 is outside the horizon, otherwise you're inside the horizon. The key point is this one. One of these polarizations, let's say it's a left-handed or the right-handed, it doesn't matter, it depends on your convention. Because they have different equations of motion, once you go find a solution, one of these T is going to have a bump, is going to increase around the horizon size. And because it's coupled to the metric, with a little delay, with a little lag, the metric, one of the metric polarization, either the left or the right, depending on the left or the right, tensor degree of freedom in the gauge sector being enhanced, is going to know about it with a little bit of delay, is going to know about it and be enhanced with respect to the other component. So that means, that means that psi left or psi right, gamma left or gamma right, depending on your notation, is going to be enhanced with respect to the other one, and we're going to get a chiral gravitational wave spectrum. That's one property. The other property is perhaps more basics, but even more important with respect to what we will get in single phase flow roll. Let me remind you of that. So in single phase flow roll, you can plot the power spectrum as a function of the wave number, or you can plot the energy density as a function of the frequency. More or less, it's the same. I remind you here that you've got a slightly red-tilted primordial gravitational wave spectrum. Slightly, remember, it was proportional to -2 epsilon, the slow roll parameters. So you can see it's just slightly red-tilted here. You've got your gravitational wave energy density. And if you try and detect what's going on, if you try and detect a primordial signal, let's say with LISA, with LIGO, with Einstein telescope, perhaps even with BBO, you're not going to be able to do that because the signal is too small at those scales because it's red-tilted, okay? Now, in the case of axion inflation, or in particular axion inflation with gauge fields, things are different because pictorially, at least, what you can get is this sort of behavior. So you can get a power spectrum for gravitational wave with a bump-like feature at the specific scales. And going back to Julien's question, he was saying, well, what does that mean in terms of your axion-like particle going down its potential? Well, because this axion-like particle doesn't have to be inflaton anymore, depending on its potential and depending on its, well, initial conditions, we can have the bump-like feature be there at, let's say, LISA scales. We can also move back earlier on. If there is enough freedom in the parameter space for this bump here to move about on the left and on the right. And so this is something that we can test for both at large scales, but also at very small scales as well. We are paying the price again of an extra degree of freedom, and that must be said every time. So we've got freedom in parameter space. And again, just by looking at the shape profile of the gravitational wave energy density, we can test these models. We can see something even at LISA and PTAs, which are about 10 to the -9 here, around this point, and even earlier, of course, as we shall see pretty soon. So this is something to look forward to when we test these models. And this is, let me actually stress a couple of things here. So I was precise when I said that this is an SU2 model, but I wouldn't make justice to the work of a lot of other people without saying that there's also a U1 model here. So remember, this gauge sector can be an SU2, but it can also be a U1. The SU2 is nice because we source gravitational waves directly with this TIJ, tensor degrees of freedom, that source gravitational waves linearly. But the U1 is interesting on its own. It has been used as a mechanism for primordial black holes. And a lot of the properties of the U1 model are shared with the SU2 model. And one of the such properties is this having a chiral signal. And why is this property shared? It's clear. And that's because we have got a Chern-Simons type coupling in the U1, in the SU2, and there's people working on the SUN version. So this is a shared property, and having a chiral spectrum is actually quite a distinct feature which comes straight from this sort of coupling. So let me just remind you, if I write down the equation of motion for this Tij, it's gonna have a different sign with respect to the polarization if you've got a left-handed or right-handed. As a result, T left differs from T right because these guys are linearly coupled to gravitational waves. As it turns out, gamma left is different from gamma right, and you end up with a chiral spectrum. Okay. Why do we care about having a chiral spectrum? Well, that's because we can test for it. And now, if this power spectrum, let's say, is peaked at large scales, CMB scales, we know what to do there. So we can use CMB tests, and what we normally expect in single field Sorol is that if we consider correlation between B modes, temperature, and isotropies, we get 0. That's because literally this quantity is proportional to P left minus P right, so that's 0 in single field Sorol. Same thing for EB correlations, so non-chirality normally. But in models such as this axion inflation width gauge fields, you end up with non-zero BT and non-zero EB. And that's what we knew as well whenever we started working on these models, but this has been made much more precise by the group in Munich. So what they did was to, first of all, identify an experiment that could tell us something about these models, and that's Lightbird. So everything you see has been done for Lightbird. This is the BT correlation, not the EB. As it turns out, BT is better at testing these models. And essentially, so anything above the black line can actually be seen. I think the black line corresponds to a polarimeter miscalibration. And they used it just to have an idea, an intuition as to what can be tested and what cannot be tested by Lightbird. Different colors and different types of lines actually are just different regions in parameter space. You can see this sigma and Kp. Kp is where the signal is picked. This power spectrum is picked, and sigma is just essentially the width of our bump, and sigma shows up here. And just to give you an idea, this Kp is the peak, and so Kp can vary widely because you've got plenty of freedom in the parameter space of this model, but sigma not so much. So if you want to parameterize this class of models with this Gaussian-like plot, the sigma here ought to be between 1 and 10. That's an order. That's where sigma lies. You cannot use sigma in your 10 to the minus 4 or anything like that. I just want to stress that. And so anything above the black line can be tested, and this is by Lightbird, and these are BT coloration. So that's what we have learned from the work of this group. This is the parameterization that they've used, but there is more. Remember when I said that, sure, these models can have a bump like at very large scales, but also very small scales. Can we test very small scales? Chirality in particular at very small scales. As it turns out, yes, and this was done even before these sort of models were known, at least partially. And the reasoning there is the following. If you've got gravitational waves which are secretly polarized, as it turns out, you need an interferometer which has a non-planar geometry. If you've got a planar geometry for your interferometer, essentially the interferometer is unable to distinguish a, let's say, left-handed polarized gravitational wave coming from the top from a right-handed coming from the bottom. So that would not do the job. But we can use the fact that we've got different interferometers at different geographic locations, and automatically they are not planar. And so if you use the combined geometry of the two, then of course you're non-planar, and you can test for that. You can test for chirality in particular. And this was work by Smith and Caldwell, and quite a while ago. And of course, there's also recent work by Lisa, and this was something completely different. They stressed something different and very interesting. What they stressed was the fact that even if you've got just one interferometer, you can still test for chirality by using the fact that essentially we are moving with respect to the cosmic rest frame. So we have a dipole, and thanks to this dipole, of course, you can test for chirality. The price you pay is that everything you're doing with respect to this dipole is proportional to the speed that you have with respect to the cosmic rest frame. So that's a factor of 10 to the minus 3, which doesn't work to your advantage, but it's actually a very interesting take on the matter. And what I didn't say, I haven't said so far, but of course, it's sort of obvious. I've been talking to you so far only about the gravitational wave power spectrum. There's plenty we can learn from that. In fact, I wanted to stress this because in this class of models have very distinctive properties. Again, this chirality being one of them. But when it comes to observables that tell you about the particle content of the early universe, nothing really beats the bispectrum non-Gaussianities. And in this model too, you've got something which is quite interesting on its own. These axion gauge field models give you very large gravitational wave non-Gaussianities. For example, let me just remind you that the way we phrase non-Gaussianity is something proportional to FNL, in this case, FNL tensor. And normally in single phase rho, FNL is proportional to the bispectral divided by the p zeta squared in this case to comply with convention. But the number that you get here is just r squared. The 10 to the 6 is not there. So it's an extremely small signal in single phase rho. Whilst in these models, you get something completely different that can be actually detected. Even Planck actually was able to place constraints on this model. And so this 10 to the minus 6 tells you that you can have very large tensor non-Gaussianities in this model. And on top of that, you can also get very large mixed non-Gaussianity. Although I promise I would only talk about gravitational waves. I just put in these slides out here to say that even mixed tensor non-Gaussianities can be large in this model. There too, single phase rho will give you R. In this case, you get 1000 R, which again is detectable even by Planck. So Planck is already placing bounds on these sort of models. And should I stop around here? Should I? Yeah. Let me actually put these slides.
Minutes in total, including questions. So
okay.
You can go on a little bit more.
Okay, I'll go a little bit more. Let me just conclude this part of the talk by saying that I hope I've convinced you that you can test, and we can test for the particle content of the very early universe, even if we artificially focus on primordial gravitational waves just by looking at those and nothing else. Already by looking at the scale dependence of the gravitational wave power spectrum, we can learn quite a lot. Essentially, if we see anything at very small scales that cannot be single phase rho, that's a smoking gun for something else. Now, I should say that there is this partial exception of so-called non-attractor models of inflation. There you don't have, you really just have a single field model, but you've got a non-attractor phase followed by an attractor phase. So that's a sort of a special case of single field models that do the job, even at small scales. But other than those models, anything else is a smoking gun for multi-field inflation. If you see anything at all at small scales when it comes to gravitational waves. So scale dependence already carries a lot of information. Chirality, of course, is perhaps the most important signature of this entire class of models. Essentially, when you have this chi FF tilde coupling, you get a chiral signal. And yes, to say something to be complete, of course, if you have the gravitational Chern-Simons coupling, so let's say phi RR tilde, you can also get the same sort of signature. And of course, non-Gaussianity itself is really the queen of observables when it comes to the particle content of the early universe. So this is sort of making the case for axion gauge field models. Now, if there are questions, I will stop. Otherwise, I can just say something slightly more general. Yes, yeah.
To repeat what you said about the scale dependence. Multi-field inflation.
What is it about the scale dependence?
Yeah, you said, if I understood correctly, that if you have gravitational waves at small scales,
very small scales, yes.
This is necessarily a signal of multi-field inflation?
No, so what I said is that this is not necessarily because there are models, including these non-attractor models, they are still single clock models, non-attractor models. So they actually can have a signal at small scales that you can actually detect. But in most cases, in order to be able to have something different at very small scales, you need a multi-field model. So if you're going to play the single phase rho game, but we all know that your tilt tensor power spectrum is proportional to -2 epsilon, and then if you put that on top of CMB bounds, you really need to go slightly down as a function of wave number or frequency, and so you're going to be below LISA, etc., below ET. The only planned experiment I'm aware of that could do the job of detecting even single phase rho inflation is BBO, but that too, as time goes by and we place constraints on R, that says it's actually very, very hard to detect anything that's single phase rho. So if you see a signal, a primordial gravitational wave signal at small scales, I would consider it almost a smoking gun for multi-field inflation. Now, all right, so this perhaps 3 or 4 minutes if I have them. Yes?
Yeah, go on.
Okay, So I should make justice with everybody else in saying that, yeah, there's a rich literature on the subject, and you will see in, say, on the archive, you will see that these sort of models have been used to, people have expanded on this type of work. Gravitational assignments has been considered, and plenty of other things. And the fact that you have actions, it sort of give you, and the fact that you have a chiral signal, give you a mechanism for gravitational leptogenesis. And there's been strong effort to try and embed these models in supergravity and even in string theory, and seems to be successful so far. But let me remind you of something else rather quickly, which is much more general. So if instead of being particularly, so I find action inflation model particularly compelling. If you don't, if you just want a general approach to the inflationary particle content, then perhaps you would start asking questions such as this one, right? How can we plot the mass and the spin of the particle content during inflation? So far, we've talked really about just power spectra. In this case, I'm defining it just by using scalar degrees of freedom. You can do it, you write down the 2-point function, and you can write down a 3-point function. There is momentum conservation, which is what this little picture represents. But when people talk about the bispectrum, it's essentially the 3-point function in Fourier space. So this is B. And one way to characterize this 3-point function is by its amplitude. So it's a bispectrum divided by the power spectrum square. This is all standard material. What I want to remind you, and I can just go through 2 slides just to give you a general picture, is the following. Let's focus on the scalar sector. Let's focus on scalar non-Gaussianity. Now, typically there is a relation between scalar non-Gaussianity in the squeeze limit and the power spectrum. This is the well-known Maldacena relation. And essentially this tells you that even when you probe non-Gaussianity, you ought to be careful, because if you calculate the leading non-Gaussianity in the squeeze limit, say in single field roll, actually what ends up being physical is not the leading contribution, not B0 here in this expression, but B2, as it turns out. So the physics information is typically actually for n is equal to 2 if you are in single field roll inflation. And this is typically much, much smaller in single field roll. And that's why we say that FNL order 1 is actually very suggestive of multi-field inflation. But what I want to stress is perhaps just this slide, which I like very much. So let me just talk about this slide and then stop. So remember, what I've mentioned so far has been the power spectrum, chirality. If we go after non-Gaussianity, we're going to go after something like zeta, 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 or gamma, 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 and so on and so forth. Now, depending on the model that you are probing, some models might have a non-trivial contribution in the squeeze limit. Some models will have a non-trivial contribution in the so-called equilateral limit, etc. Now, the squeeze limit corresponds to the limit. It's a soft limit, essentially. So one K is much smaller than the other 2. The equilateral case is all Ks are roughly of the same order. Now, whenever your model has a non-trivial squeeze limit, then things become particularly interesting. Okay, so why is that? Well, let's say you have your model. It's a multi-field inflation model. You calculate squeeze non-Gaussianity, let's say scalar non-Gaussianity, just because it's simpler. You end up with something like this. This is forced on you. You don't have a choice. Under very general conditions, this is the sort of results that you get. Okay, so let's look at this result. You've got a standard contribution that you essentially get by dimensional analysis, 1 over K long cubed, K short cubed. And then you've got this very nice K scaling. So if you're on the squeeze limit, remember this is K long and this is K short. And the exponent here is really quite interesting because it's not 3 halves, it's 3 halves minus nu, and nu knows about your particle content. Nu knows about the mass of any extra field you have during inflation, and it also knows about the spin of any extra field you have during inflation. So this is quite interesting. From the K scaling of your squeeze non-Gaussianity, you learn a lot about the mass and the spin of the extra particle content. Now, on top of that, you've got this PS, this is a Legendre polynomial, and S stays there for spin. So from the angular dependence of your squeeze non-Gaussianity, again, you can learn quite a lot about the spin of your particle. So if you have a scalar, you get a boring constant, but if you have a vector, you get P1. If you've got a spin 2, you get a P2, and so on and so forth. So even though what I said so far was stressing the power of, sorry for repeating it, the power of the power spectrum of gravitational waves to tell you a lot about inflationary particle content. For axion gauge field models, as it turns out, that's plenty to tell you what's going on. But if you want to be general, if you want a queen of observables when it comes to the particle content of the eddy universe, then you need to look no farther than the squeeze limit of the power spectrum, because it has plenty of information on the mass and spin content of any extra particle during inflation. So mass and spin are here, and spin is here as well. And let me remind you that if you've got single field swirl, then here you would just have analytical scaling, meaning an integer power here. Well, if you have extra fields, you end up with something non-analytical and directly physical that you can test for. So there's info on mass and spin here. I said everything about the scalar, and just to prevent any question, I should also say that if you want to get inventive and consider, let's say, mixing on Gaussianity and so on and so forth, these are really the same. It's really the same physics you get, sort of similar scaling, similar behavior. Yeah, this is just the polarization tensor. But I don't want to say anything more because otherwise I run out of time. So I'm going to just skip 500 slides. And no, this is not at all. Well, let me just say, yeah, conclude by saying that sure, because we are lucky, cosmological probes are going to soon cross qualitative thresholds for R. Remember, R 10 to the minus 3, Sarobinsky inflation, and so on and so forth. Was no time to go really properly through the info we have on FNL, but we're going to reach FNL order 1, which is right there, the watershed value between single field and multi-field inflation. But I would say that because this is coming, it's a great time. So there's plenty to do on the theory side, so we can explore compelling models of inflation and put forward new ones if we are inventive enough. But also we ought to build a theory to data pipeline to test this inflationary particle content. Well, at reach, it's the usual thing that people write on grants, deeper understanding on the early universe and all, and like that. But it's true that if we detect primordial gravitational waves, then we do have an immediate connection with very high energy particle physics. It's the only portal that we have at those energies. And I would say that it is the usual, the point that we always find ourselves, that we have to study what's compelling, but sometimes what's compelling is not really testable. But if we're doing inflationary model building or inflation in general these days, I think there's these two sets really overlap, and the intersection is not empty. There's plenty of compelling models that can be tested. And let me just leave you at that, and thank you. Yes.
Yeah, you told me that this spin 1 degree freedom can be a source of spin 2 perturbation, the gravitational wave. Yeah, the gauge field.
Yeah, so
it can be a source of the gravitational wave.
Yes. In
and the part I couldn't understand that also. Can you be more kind on how is it possible?
Yeah, so I like this question. So in the case of SU2, I hope I've convinced you, right? That because you've got tensor degrees of freedom, the sourcing is linear. There's no question about that. For the U1, it's different, right? So for the U1, in order to source gravitational waves, you have to go at loop order. So you've got this, let me write down, you've got gamma, and then you've got A mu and A mu here. Okay, can you see? So this is the way you source primordial gravitational waves in the U1 model. And interesting also, you can also source scalars in the same way. So in the case of U1, the way you source gravitational waves and the way you source scalars is actually the same, but you have to do it through loops. Essentially, because if you want a diagram that involves gamma or zeta here, the only way you can source them is just by going to loops. And this might come with a question, but this question has already been solved, I should say. And this was one of my questions as well when I studied the U1 models. You say, if you have to resort to loops when you're going to source primordial gravitational waves, what about 2 loops and 3 loops? I mean, is this perturbatively consistent? And as it turns out, there's work by, I think, Barnaby and Peloso. And what they show is that, yeah, when you consider the 1 loop, you've got the leading contribution is actually coming from a 1 loop diagram to gravitational waves. But what they prove is that if you go to 2 loops and higher order, no, the contribution goes down. So it actually is perturbatively consistent to go at 1 loop. So the 1 loop is spatial in this model, but if you go to higher loops, the contribution, of course, goes down, and perturbativity is okay, it's consistent.
Spin 1 source.
No, but in the SU2, you've got these tensor degrees of freedom, right? You've got this Tij. No. So that's the key, right? The fact that you have an SU2 means that you can switch on the background in the SU2 case. And if you just split all your degrees of freedom, you end up with this Tij. This Tij is tensor degrees of freedom. So you can write down a diagram just by symmetry. You can write a diagram with gamma here, and let's say, let me draw it like this, Tij, right? So this is linear, and you're sourcing gravitational waves linearly. So you can do something like gamma ij, Tij, and this is different from 0, but you cannot do a gamma ij, a mu, right? You get 0 right away if this is a U1. Because if this is a U1, you don't have tensor degrees of freedom right there for you. You just have a mu, you just have a vector there, and you get 0. That's why you have to resort to loops. But if you use loops, you can do it. And in fact, I should say that in the SU2, gravitational waves phenomenology is more interesting, in my opinion. But if you want to, for example, come up with mechanisms for primordial black holes, if you're really interested in sourcing the scalar sector, then you need to go U1. For the U1 gives you a richer phenomenology on the scalar side of things. So, different uses for different models.
I had a question on the here. So on the first scenario that you're talking about, there is an inflaton field which is inflating the universe, and then there's the action field. So in some sense, like a curvaton-like scenario, and typically you also get some sort of local non-Gaussianity from the curvaton, like depending on like when it decays and so on. So do you also have that in an interesting regime where you have some bumps in the gravitational wave spectrum and you also have some local non-Gaussianity?
Yes, you have interesting, but the type of non-Gaussianity that you have is equilateral. So yeah, so in fact that's the one key difference for these models. Essentially, because you have derivative interactions, you get a non-Gaussianity which is equilateral, and we would have loved actually to get a local signal, because there's many ways to test the local signal, and as I showed in the slide, squeeze non-Gaussianity carries a lot of information about the particle content in general, but we have calculated the signal in the squeeze limit, and that's 0. So in these models, there's no squeeze signal, and I believe also in the U1 that's the case. So only equilateral, so which is great because you don't have to worry about consistency conditions or anything like that. But at the same time, all this info on the scaling with the wave number that you get in the squeeze limit, we don't have it because the signal in that configuration is not there.
So there is a question on Zoom. So the person who raised their hand, please go ahead.
Hi, can you hear me?
Yes.
Yes.
Okay, so I was wondering why you didn't have the interaction between chi and inflaton. Why didn't you put the interaction between chi and the inflaton? Did you?
So yeah. Why did I put it or why I didn't put it?
Yeah. Why didn't you put it?
Oh, so initially, let's go back quite a while. So let me just go from here to here. So because typically we indicate the inflaton with phi, so here what we did was to change, and we didn't call it phi, and phi is here. This is again the action, but it's not the inflaton anymore, if that clarifies. So the fact is that in this slide, we did not want the action-like particle to be responsible for inflation, because if it is, we essentially go back to these slides where everything works out extremely well, except for the fact that you overproduce gravitational waves, and therefore we were forced to add an extra sector. This wasn't really a choice. We were forced to do it because otherwise we have tension with the data. We have tension with Planck because we overproduce primordial gravitational waves. Essentially, in order to get the right scalar spectral index, you have to crank up lambda to very high values. You've got gravitational wave signals, chirality, and everything. But if you calculate R is too large. So in order to have R that is not too large, what we do is, add an inflaton sector. The business of inflating is taken care of by this one. And so the NS-1 is entirely a responsibility of the inflaton sector. And on this side, We just use this site to have an interesting gravitational wave phenomenology. I think he's asking why you don't put a coupling. Oh, well, we don't in this model because we wanted to, okay, thanks for clarifying. We didn't because we wanted to keep the model simple, but I should point to work by Soda and Obata. So Soda and Obata put, I believe, an I of phi here, where we've got, yeah, they consider this type of coupling as well, and they can generate interesting signal also at small scales. So this has been done, and I should also say again that for completeness that there's work by Dall'Agata, who was trying to embed Chromo natural in supergravity, whereby this coupling comes out naturally from the supergravity construction. So this is something that's interesting. It has already been done. Yes. So yes, in the SU2, so yes, so crucially in the SU2, first of all, that there's less of a worry because we don't, in order to source gravitational waves, we don't need to resort to loops, right? Because this TIJ intervenes already at the tree level. But it is true that even in the case of the SU2, you've got loop contributions to both the gravitational wave power spectrum and the scalar power spectrum. And in fact, I do have a slide for this. Actually, I have a slide for the constraints that are coming from this perturbativity bounds. If I find it among these 500 slides, yes. So what you have here looks a bit messy. I apologize, but this is essentially the parameter space of the model, and we are avoiding back reaction. We want to have the chiral signal and everything. We are pushing H to be large because we want to be able to detect primordial gravitational waves. And so the effect that you get, once you consider all these perturbativity bounds, what happens is that normally your source contribution, your source P gamma could be orders of magnitude larger than the vacuum fluctuations. Whilst once you put all of that in, you can say at least there is at most one order of magnitude between the two. So that's been considered, and it does reduce the parameter space. Yeah.
Not, let's move on. Speaker.